Welcome to a video for section 2.3 from Math 1, which is on patterns and nonlinear functions. So to begin with, let's go ahead and take a look at graphically what the difference is between linear and nonlinear. Alright, so a linear function is a function whose graph is a non-vertical line or a part of a non-vertical line. So think just, it looks like a line. Vertical lines can cause problems, and we'll discuss that later, which is why we're not including them. But every other line would be a linear function. So we have this kind of a line, we have a flat line, and then this line. Okay, these are all lines. We saw an example in the last video where it wouldn't make sense to connect the dots. All right, and we called this discrete, but it's still a linear function. Okay, nonlinear functions, when you graph them, make things that are not lines. Okay, you may know what these are called, you may not. This is a curve, it's not a line. It's specifically called a parabola. You'll learn about that later in Math 2. This is also a curve, it's not a straight line. This is called a cubic function. You'll also learn that in, I believe, Math 3. And then this one, we're probably going to talk about this here. This is an absolute value function, and this is another example of something that is discrete, where we're not going to connect the dots. Usually word problems that don't make sense to connect the dots are going to have graphs like that. Okay, so the definition is pretty much it's not a line, it's something else. Okay, all right, so we're going to look at a couple examples of things that turn out to be nonlinear functions. So let's go ahead and take a look at the first example. The table shows the relationship between the number of steps in the staircase below and the number of blocks needed to build the staircase. Copy and complete the table. Is the relationship a function? If so, is it a linear function? Okay, before we do that, let's just remind ourselves what it means for something to be a function. We did this in the last video in 2.2. Basically it said one input matches onto exactly one output. You may remember we talked about the function machine, right? You have this machine that you put stuff in and it spits out a number. Okay, so you put in your input, which are your x's, something happens, which is the function, and you get out a y. And if you were to get out, let's say you plug in 5 and you get out 7 and you get out 9, that's a problem. That's not going to happen in a function. All right, so you only should get out one number, maybe like a 7. Okay, so let's go ahead and take a look at the table. I guess I don't really need all this right here. Okay, so the table says we have a number of steps. It might be a little hard to read. That says number of steps, number of blocks, and ordered pair. So the number of steps, so here we have one step. Here we have 2 steps. So 2 steps, notice we have 3 blocks. Okay, so with one step you just need one block. So here's the number of blocks, here's the number of steps. Okay, the 2 steps, so to go up 2 steps you still have, you don't just use 2, you have to use a third one as a sort of stabilizer right here. So with 2 steps we have 3, so you can see 2 steps and 3. 3 steps, up 1, 2, 3 steps. If we count how many blocks we use, I see 1, 2, 3, 4, 5, 6. Okay, so we need to complete this table. It says 4 steps. Well, you can draw the picture. Imagine 4 steps, up 2 steps, 3 steps, 4 steps. Okay, now imagine how many blocks that is. So here's 1, and then this row is going to have 2, and then we're going to have 1, 2, 3, and then this one's going to need to be 4. So let's count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. so the ordered pair would be 4, comma 10. At this point, maybe we should be thinking if there's a pattern going on here. For every step that we go up, see we go up one step each time. Let's see how many blocks we're going up. Here we're going up 2. Okay, and then we're going up 3, and then we're going up 4. Okay, so we can see that we're going up one more each time. So that's one way you can think about it. But in the next step, we're going to have to well, let's actually go back a step, and answer the question, which is this a function? I think it is. In fact, I know it is, because we're only going to get one answer. We plug in a number, we get one number. We plug in a number, we're going to get one number. We're not going to get two numbers. You can't have steps with 2 and you're going to make it with different blocks, right? A different number of blocks. If we have 3 steps, we're going to only need 6 blocks. So everything's matching up 1 to 1. So that's perfect. So I would say yes, this is a function. So yes, this is a function. All right, what else do we need to do? All right, we still have to do the fifth step, but maybe you can already figure it out. We know we were adding 2, then 3, then 4. So the next one we should be adding 5. So that would be 5, 15. Okay, so let's do a graph and decide if this is a linear function. So on one axis, our x-axis, we're going to have the number of steps, which is our x. So we looked at 1 steps, 2, 3, 4, 5. Okay. And then here we're going to look at the number of blocks. And for this we need to get up to 15. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this isn't enough to go by ones. So maybe we can go by twos. So 2 blocks, 4 blocks, 6, etc. 8, 10, 12, 14, 16. Okay, so let's plot these points, and we can see what the graph looks like. Graphing it is one way to determine if something is linear. It's not the only way. All right, so 1 step, 1 block. So 1 block would be halfway in between. 2 steps is 3 blocks, so halfway in between 2 and 4. 3 steps is 6 blocks. 4 steps is 10 blocks. And 5 steps is 15 blocks. Does this look like a line? Well, you can take a ruler, and if I were to go through 2 of those points, this would be a line. So it's not linear. In fact, it looks like it's curving. Now, I'm just going to draw over this temporarily just so you can see the shape, but these are actually, this doesn't make sense to be connected because these are discrete. You can't have like 1.5 steps, but I just want you to see the curve a little better. But now I'm going to get rid of that because that shouldn't actually be connected. Okay, so this is non-linear. So graphing is one way to see that. Another way to see that is by looking at your table. Remember in the last video we talked about how linear each variable, the independent and the dependent variable, is going to change at a constant rate. So here we could see we're going up 1, up 1, up 1, up 1. So this is a constant rate because these are changing at the same. We're just going up 1 each time. And as we already saw, this is not going up at the same rate. It's changing. Up 2, up 3, up 4, up 5. It's going up at different rates. And so that makes it also nonlinear. Okay? All right, let's look at example 2. Pizza. The area A in square inches of a pizza is the function of its radius r in inches. Okay, so graph the function shown by the table. Is the function linear or nonlinear? Okay, so we've got our different variables this time. Instead of an x and a y, we have an r and an a. And many times in word problems, we change the variables to reflect what we're talking about. Okay, so we're talking about a pizza, a circular pizza that has a radius r and an area, so the area is how much pizza there is, of a. Okay, so let's make a table. So our independent variable is the radius of the pizza, so I'm going to let that be the r-axis instead of the x-axis. So we need 2, 4, 6, 8, and 10. So we can go ahead and just go by 2, 4, 6, 8, and 10. All right, let's look at our area. Our area ranges all the way up to 314, and its lowest is about 12. So we're going to have to go by something fairly high, maybe even 50s. Let's see. What I like to do when I figure this out is I count how many lines that I really have space for, and I divide that by the range I need to do. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So if I did them by, let's say I did them by 20s. 20 times 12 is 240. So that's not big enough. So I need to go bigger than 20s. If I do 25s, 25 times 12, that's a little bit harder. That would be, well, 25 times 4 is 100, and 12 is 4 times 3, so this would be 300. That's closer. Okay, let's go by, I think going by 25s is enough. We just have to go a little bit higher. Okay, so I'm going to go by 25s. It'll go off the graph a little bit, but that's okay. So 25, 50, 75, 100. And you don't have to write them all, you get the idea. But maybe let's figure out where 200 is. So 125, 150, 175, 200, 225, 250, 275, 300. So maybe I'm just going to extend it 1. And here's 325. Make one line. Okay, good enough. All right, so let's plot it. So 2-inch radius is 12 inches, or 12.57 square inches. So 2-inch radius, so that's about halfway in between 0 and 25. 4 would be about 50, so we can put it very close to the 50. 6 would be 113, so here's 100, here's 125, so somewhere in between there. 8 would be 201. And 10 would be all the way up to about here. So do you think this is linear? I would say this is nonlinear. It's making a very steep curve. Now this one we can actually connect the dots because you can have a pizza with a decimal radius, like it could be 1.74 inches in radius. So it actually makes sense to connect. So I'm going to go ahead and make the curve best I can. It's a little hard with what I'm using, but that's good enough. Okay, last example. I want you to try this one on your own to the best of your ability, but first I'm going to show you what we should label our axes just so that we have the same thing. So we're looking at number of blocks on edge. So just to make sure you understand what that is. Okay, here's 1 block on edge. Here's 2. Here's 3. So that's the edge that they're talking about for this X right here. And then total number of blocks. Imagine this in 3D. We're counting, like, this is 1 block right here. In this one, here's a block, 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 here's a block. But then you have to imagine the ones that are behind that you can't see. Okay, so imagine the whole thing, hold it in your hand like a Rubik's Cube. Okay, so that would be our y. All right, so our y is going to be total number of blocks. Okay, in this one, we're going to need to get up pretty, it's going to get pretty big really quick. So think about going by maybe something big. I'm gonna, let's once you decide what you want to go by once you get your numbers. And then this axis over here is going to be the number on the edge. Oops, right here. Okay, the number of blocks on the edge. And this one we can just go by ones because we have 1, 2, 3, 4, 5 in the t-table, and that's it. Okay, so go ahead and pause the video, try and figure out the rest of the t-table, try to represent the relationship that you're noticing in words, try to come up with an equation, and then graph it. Okay, so I drew out, to the best of my ability, what it would look like if you had a 4-edged cube like this. And it's going to be a little bit more difficult to figure out like where, like you have to imagine how many blocks are there. So you might want to start thinking about it in layers. So in one layer here, the front layer, there are 16 blocks. Okay, but then you have to imagine there are 4 layers total. Okay, so we have 1, 2, 3, and then 4 layers. So if you do 16 blocks times 4, you can get that there are 64 total blocks in the whole figure. At this point, it might be helpful to realize what's happening here. 1 becomes 1, 2, 8, 3, 27, 4, 64, 5, 125. These are perfect cubes. So we're talking about like 1 cubed. So that means 1 times itself 3 times. That gives you 1. Okay. 2 cubed. Okay, 2 cubed is 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. 3 cubed is 3 times 3 times 3, gives you 27. So that's what these numbers are. They're cubes. So 5 cubed, which is 5 times 5 times 5, is 125. 4 cubed is 64. Okay, so that helps us with an equation. Y equals, which is the total number of blocks that you get, equals the number of blocks on each edge, or x, to the 3rd power. This is the equation. So we can write that as the number of blocks on the edge, and then you can say cubed, or you can also say to the 3rd power, which means the same thing, equals the total number of blocks. Okay, so you can see I already graphed it, and I'm not going to connect the dots again because you can't have half a number of blocks. It doesn't make any sense, but you can see that it's not making a line, it's making a sharp curve just like before. All right, that's it.